This is part 1 of the Chapter 3 summary for the Deep Learning book, authored by Ian Goodfellow and others as presented on screen here. This chapter is about probability and information theory. As I mentioned in my kickoff video, I'm coming at this from an undergraduate industrial engineering background perspective, and that's being educated in Ontario. And so the probability portion of this chapter was mostly a review with some important things that were new to me, and the information theory was basically all new to me. So we'll get to the information theory in the following video. Probability theory comes first in this chapter, and so we're doing it in sequence as the authors present it within their framework. A brief description of probability theory is here. I think that the last statement here is the most important to really chew on. It's the idea that having the robust mathematical theory of probability is about being able to express the uncertainty of one possibility using a relationship that uncertainty has to another uncertainty of a different event. So just as with mathematical theories in general, it's the defining of relationships that allows us to make more with it, that allows us to get more data out of a situation. Its application to AI is foundational. AI is an imperfect tool in virtually all cases, and that's by design, of course, because it's often applied to situations where no perfect, optimal analytical solution can be computed. It's only natural then that the solution or decision arising from an AI system has some sort of level of confidence associated with it, some level of uncertainty. And that's why probability theory is so intrinsic to getting these systems to function. In addition to that, probability theory can be used to theoretically analyze behavior of a proposed system before implementing it. So naturally, probability is centered around the idea of uncertainty, so it's good to know that uncertainty actually has different sources. The first is when it's inherent in a system. For example, let's say you wanted to make an artificially intelligent program to play poker. The fact that cards are shuffled randomly in the game is intrinsic to the definition of the system within which the agent is operating. It couldn't be any other way, so there is a source of uncertainty there. The second source is incomplete observability. The idea here is that a system could be deterministic in reality, but not appear deterministic because the observer doesn't have all the information. This creates a different scenario as compared to true randomness. An example could be streetlights at an intersection. Say they're programmed to change every 2 minutes, or after a car has been waiting to make a left turn for 30 seconds, or 20 seconds after a pedestrian presses a button. If an observer could only see the light, then these different triggers for the light to change would cumulatively make the changes appear to occur at random intervals. The third source of randomness or uncertainty is incomplete modeling. This refers to times where information is available or known to be available but not taken into consideration, perhaps due to lack of feasibility or capability. For example, say that a real and continuous value is measured from a sensor, but it's rounded down when stored in computer memory. If the computer is then tasked with returning the real value, it can only return the rounded down value that is stored as the best guess. That's all it has. And the error resulting from this best guess, the difference between the input and the output, might be considered random if no other information is available. So the randomness came from losing data that was present. This final source of error is really important as it becomes relevant when using heuristics. Heuristics essentially are incomplete models. They naturally categorize output or action based on potentially disparate input. Heuristics can be desirable in machine learning because they're cheaper to develop and more broadly useful than a highly specific rule or function, even within a completely deterministic environment, where a perfect but intensive rule or function could exist. It's about computational efficiency in some ways. Broadly, there are two types of probability, but they're treated in the exact same manner with respect to the mathematics involved. Frequentist probability relates to the rates at which events occur, whereas Bayesian probability refers to qualitative levels of uncertainty. Probability is only ever a value between 0 and 1, with 0 being certainty that an outcome will not occur, and 1 being complete certainty of an outcome occurring. Random variables can be either continuous or discrete. A discrete variable is one that can take on finite or countably infinite states. It's important to note that the state it takes on doesn't have to be a number. It could be a named qualitative state, for example. A continuous random variable is one that takes on numbers as its values, and that takes a random value from a non-finite or non-countably infinite state. To get a sense for the difference of these two, You could think about the fact that the set of all integers is countably infinite. After all, what's the highest integer? There isn't one. For any integer you pick, you could just say that plus 1. You can go higher. But consider the same question for any real number that's integer or not. The fact is that if you try and count every real number between 0 and 1, you can't even do that because the decimals could go on forever. So hopefully this idea gives a feel for the qualitative difference between countably infinite and non-countably infinite. I would just recommend you do further research if you want to understand that better. On the right side of this slide, you can note the convention for referring to random variables in the text. So moving on, probability distributions are the functions that describe the probability that a given outcome will occur for a given variable. They differ between the different types of random variables, continuous and discrete. Discrete variables have discretized probability distributions, where each possible random value has its characteristic probability. For example, when you roll a theoretically perfect dice, you have a precisely equal chance, 1 out of 6, of rolling any of the 6 numbers. The implication of that is that there is no chance of rolling, for example, a 1.5. It just isn't possible, as it's not in the set. On the other hand, continuous variables have probability density functions, which are also continuous, and allow for computing the probability that the random variable will take on a state within a given range. On the right is some notes about how things are written as it relates to these. One thing to note is the difference between probability distribution notation and function notation. Whereas a function is always constant, and the argument it takes on goes into the brackets beside the function name, probabilities are the opposite in a sense. They're typically referred to by capital P around the variable name. And so these should not be confused, since the P can refer to different distributions for different variables. We'll look at each of these PMFs and PDFs in some more detail. So each of these types of distribution functions has certain characteristics that define and distinguish them. These properties can be understood as natural constraints, which follow from thinking about the nature of probability and sets of outcomes. For the first, it's obvious that if there is some outcome, some state that a random variable can take on, there simply must be some probability associated with that occurring. The second is a rationality constraint. There's no such thing as a probability greater than 100% or less than 0%, as that would just be nonsensical. Lastly, a frequentist approach allows for making sense of the third constraint. Consider if you ran 100 trials of a test and had, say, 2 or 3 outcomes of varying frequencies. The probabilities for those outcomes could be, for example, 20 out of 100, 75 out of 100, and 5 out of 100, if that's just what you recorded from running the test. But whatever those were, the fractions would have to add up to 100%. Another way to think about this is because some value must be taken on by the variable, and so the entire spectrum of probability must be covered by the possibilities of the different outcomes. A PMF, probability mass function, can also describe the probability of multiple variables taking on given values at the same time, which is denoted as seen on the right. So that's a joint probability. The example on the bottom right applies to dice or card shuffling example, where the probability for selecting any item from a random set is equal for all items. And so it's just equal to 1 divided by however many items there are in the set. So naturally, probability density functions, or PDFs, have similar properties as compared to PMFs. The first is the same. The second notably does not have a limit on the upper bound of the value of the PDF at a given point. This doesn't indicate a deviation from the same rational logic we saw before, though. That constraint on being less than 1 has simply been translated, in a sense, and subsumed by the third constraint. If you recall that the integral yields the sum of the area under a function, then it's obvious that fulfilling the criteria of having the integral of the PDF equal to 1 meets the same rationale as was developed earlier. It's important that the PDF can be of a value greater than 1 at certain points, because this allows for modeling real-world scenarios where the probability might appear exponential, and PDF might have an infinite limit case. In those situations, integrating over small areas can appropriately yield the results of very high probabilities, depending on the scenario. It's really important to understand that the PDF is never used to compute the likelihood of a single discrete value. That's because it only applies to continuous values. You could think and understand this from the frequentist approach. You might say that the probability of a given outcome is equal to the PDF at that outcome. But if you're interested in the probability of the value being 2, for example, then you must specify whether you mean 2, 2.0, or 2.000, or 2.0000, etc. The problem could be understood as the fact that you can't identify a single value to infinite decimals in the continuous range. So that's why probabilities are not computed for single values. Instead, they're only computed on intervals. By summing the area under the PDF on an interval, you get the probability that a random variable would take on a value within that interval. As stated on the right, it's key to note that the probability of a single hard value is actually infinitesimally small for PDF, and in practice, probabilities are only ever taken for a variable to fall on a range. Marginal probability is the idea that you can compute the probability of an outcome for a single variable in isolation if you have the probabilities of that variable occurring jointly with other variables. For example, say you were drawing 2 marbles from a bag at a time, and the bag had 1 marble for each color in the rainbow. If you wanted to compute the likelihood of having 1 blue marble in your hand, then you would have to add the probabilities of the different draws that have a blue marble. For example, add the probability of drawing a blue and a red marble, and the probability of drawing a blue and a yellow marble, and that of drawing a blue and a green marble, etc. That's the application of marginal probability. The same applies for a continuous joint probability function. By fixing one variable at one value in a continuous joint probability function, the two-dimensional function compresses to a one-dimensional joint probability function and can therefore be integrated. Conditional probability refers to the probability of a variable taking on a value, given that another variable has taken on a certain value. This is a really important idea in probability theory, as evidenced by the frequent problems framed with a given, such as, what is the chance that rain will fall today, given the cloud cover is dense today? It should be noted that though conditional probability and its computation doesn't have anything to do with causality of A causing B or B causing A. Just because something has a conditional probability doesn't mean that two events are dependent on each other or independent. I find it easiest to understand and recall the formulas for conditional probability by conceptualizing the possibilities of outcomes as areas of an outcome space. So you can think about each circle representing the collection of some values that a variable could take out of the total set of possible values for any variable, which is encapsulated by the rectangle here. In this frame, you can think about conditional probabilities as the probability of being inside of one area, given that you're inside of another area. So looking at A and B, the probability that you're in A, if I give you the fact that you're in B, is 100%, because all of B is inside of A. In the reverse scenario, the probability that you're in B, knowing that you're in A, is equal to the proportion of area of A that B covers up. That's how you can make sense of the formula. One handy tool is to be able to represent a joint probability as a sequence of conditional probabilities, which relate back to the probability of one of the variables in question. In the frame of conditional probabilities as areas we saw on the last slide, this can be roughly interpreted straightforwardly as starting with the probability of being in one area, and then multiplying that by the fraction of the area that the next area takes up, and so on. It's kind of a rough analogy though. Variables are independent when the values they take on have no bearing on one another. When this is the case, the probability distribution function is just the product of their respective functions for each value. You might think of dice rolling as the classic case, where rolling the same number twice is just equal to the probability of rolling the number squared. Conditional independence describes a situation where random variables are both considered in light of a given piece of information. Having that given information changes the probability distribution of each variable to being a conditional probability function based on the new data. If the new conditional probability of x given z is the same for all values of y, and vice versa, then x and y are conditionally independent. It's clear that this could happen with an example. Say that a random variable x is the time it takes for person A to get home from work, and a random variable y is the time it takes for person B to get home from work. And these are two people that live in the same city but in totally different neighborhoods and workplaces. If z is the state of the weather, then getting home in time for dinner is related to the weather for both individuals. But even given that mutual dependence on the weather, the facts of whether or not each one gets home in time for dinner are still independent of each other, given that their roots have nothing to do with each other. So they're dependent on the same variable, the weather, but they're totally independent of each other. On the other hand, as it states here, variables are conditionally dependent if knowing some other information changes their probability with respect to one another. For example, let's say x and y were the result of two dice rolls. Knowing what x is doesn't tell you anything about y, because they're independent, different dice. If, however, you're told that the sum of both dice was an even number, then this extra data constrains the possibilities of what the unknown y can be. Since the probability distribution function is changed by the new information, these random events are not conditionally independent with respect to the condition z. Of course, one of the basic components of probability theory is being able to compute an expected value for any distribution. The formula is different once again for discrete and continuous variables, but the basic idea is the same and can easily be understood as summing all possible outcomes, but giving each a weight according to its likelihood. It should be noted that based on this calculation, the expected value for a discrete probability function can actually be a value that the variable will never take on, such as a fraction. That's a result of the averaging out that occurs. The expected value is the value you could use to minimize your overall guessing error if you had to guess a random variable, say 10,000 times. Mathematically, it's important to note that the expected value as a function is characterized by linear function properties, so that includes that scalars can be factored out, some terms can be separated, and some others. As mentioned in the last slide, the expected value is the one which, if consistently selected as a guess, would yield the minimum error over time. The variance can then be thought of as the factor that determines the scale of that cumulative error. If a probability distribution is really wide, the error will be large if you consistently guess the expected value as a random variable. But if a probability distribution is narrow, your error will be smaller if you continuously guess that the random variable will take on the expected value. So variance gives a sense of how wide a distribution is. It's defined as the expected value from the collection of values resulting from subtracting each potential outcome from the expected value of the distribution and squaring it. Kind of a mouthful. Beyond that, variance for a probability distribution can actually be thought of as the covariance between a variable with itself. The covariance is used to measure how two variables vary with respect to one another. It's important to know that covariance and independence are different but related things. They're related because independent variables have zero covariance and dependent variables have non-zero covariance. Independence is actually a stronger position than zero covariance because independence means there's no relationship between variables, while zero covariance means there's only no linear relationship. This slide is from my last video where I reviewed the vector covariance equation in more detail. And the one thing I'll point out again is that it's important to understand what a covariance matrix is. It's a matrix where each element at coordinates I, j represents the covariance between two variables based on its indices I and j. So for a multivariable system, the covariance matrix contains all covariance values within the system. You can see my previous video for more review of that. Being able to conceptualize what numeric measures of variance or covariance mean is critical to deeply understanding many things in probability theory. The standard deviation is one tool to do this. It's the square root of the variance. The value itself will change for a given distribution, but for all distributions, the interval either up or down between the distribution mean and one standard deviation captures 34.1% of distribution outcomes. And this is actually just for any normal distribution. As we'll discuss, this is very handy to know since normal distributions are widely used. And as can be seen on the right, The value of covariance can be understood to indicate how strong the presence of a linear relationship is between two variables. A negative covariance indicates a negative linear relationship, and vice versa. A zero covariance indicates no linear relationship between variables. But it's important to know that this method leaves us blind to the possibilities of nonlinear relationships existing in the data. These same interpretations apply to correlations as well as covariance. Next, we're going to look at some common distributions. The first is the Bernoulli distribution. For context, it's important to note the basic idea that there are these different categories, or you might say species of distributions, each with characteristic parameters, and these parameters uniquely identify a specific distribution within its family, or species, you might say. So a random variable that is Bernoulli distributed only ever yields a 0 or a 1. Here I'm showing that with set notation. It has one parameter, phi, which takes on a value between 0 and 1, and that's the probability that the variable takes on value 1. Naturally, 1 minus phi is the probability that a distribution yields 0. The multi-Bernoulli distribution is a distribution for a single variable with a discrete number of potential states. It can only be used when the variable state is not numerical. It can be used when the variable state is non-numerical, or it can instead be used when the variable state is categorical. What this means is that the states the variable takes on could be anything within a discrete set, and it can be useful to use category labels as the elements of that set. The variable doesn't just have to take on random numbers. The parameter for this distribution is a vector containing the probabilities for various states. As an example, you could use this distribution to model the probability for the color of cars passing on a road. If a given observation of a car is a random variable, then the states it can take on are the different colors that car could be, and the distribution is parametrized by the probabilities observed for each. Normal distributions are the most commonly used for real numbers. They're also known as Gaussian distributions. The probability distribution function for Gaussian distributions is pretty bulky, so standard reference tables are often used in general engineering usage. But this is an important consideration for AI, where specific values might have to be computed repetitively, so economy of computation comes into play. The parameters are mu, which defines the mean, which is where the central peak of the bell lies, and sigma, the standard deviation, which defines the broadness of the bell shape. Also, it's really important to understand that any normal distribution defined by some specific parameters can be transformed by some normal distribution to some normal distribution characterized by other parameters. This is commonly used to great effect to transform a normal dataset into a standard normal dataset, which is characterized by mean 0 and variance 1. Here I also wrote that it can be characterized by mu and beta. This is just an alternative formulation where beta is equal to the standard deviation squared. And the reason that this is done is to simplify the computation and make it more efficient, for the reasons I mentioned earlier. With respect to its broad usage, the normal distribution makes for a good choice for many scenarios, for two reasons. The first is that, according to the central limit theorem, the sum of many independent random variables is approximately normally distributed. So that means that in practice, even when a system constituents might be accurately modeled by distinct variables, the overall system can be modeled as normally distributed noise. The second reason is that, out of all possible distributions with the same variance, the normal distribution encodes the maximum amount of uncertainty over the real numbers. This makes using it a conservative option that assumes the least amount of prior knowledge into a model. The normal distribution can also be generalized to an n-dimensional space of real numbers. The univariate and multivariate expressions are presented here. In the multivariate case, a vector is used to store the mean values in the different dimensions, and the covariance matrix for the different variables is used as the variance parameter. Again, in the multivariate case, the computation is made more efficient by avoiding the inversion of a matrix every time and using the inverted parametrization off the top. The authors also note that the covariance matrix is often fixed to be diagonal, meaning the covariance between variables is 0, indicating the variables are all independent of one another. An even more simplified version of this entails setting the covariance matrix simply equal to some scalar multiplied by the identity matrix. This is called the isotropic Gaussian function. We'll see an example of this later, but essentially it means that the variance is the same in all directions. The exponential function is useful as it creates only positive random variables that spike near zero. The indicator function within the expression there means that the value of the coefficient is 0 for any value of x less than 0, and 1 otherwise. So this is how the random variables only occur greater than 0. The lambda parameter modifies the degree to which the plot spikes at 1. The greater the lambda value, the sharper the spike. The Laplace distribution is similar. It's symmetric as opposed to only one-sided, but it creates a probability spike at an arbitrarily selected point. Earlier on, it was mentioned that the probability of a continuous random variable taking on a single value cannot be computed using integration, and that probabilities are only computed over ranges. The Dirac function creates a different situation, where individual points on a continuous range have a set probability associated with them. It's important to note that the Dirac function isn't actually an ordinary function, which maps input to output. Instead, it's a different kind of mathematical object called a generalized function. The function is equal to 0 for all inputs except for 0, where it's equal to 1. It's defined based on its properties when integrated. Following from this, by using the parameter mu, we can make the function return a 0 for any value except that where x equals mu, because the Dirac function returns 1 when the argument is 0. Building off of this, the Dirac function can be used to create a strictly empirical distribution. When I say strictly empirical, what I mean is that the distribution will not yield any value that was not actually observed in a dataset. This is as opposed to assuming normality for a dataset, for example, and then referring to a normal distribution characterized by the same mean and deviation as the dataset as the empirical distribution for that dataset. That kind of process could generate values not seen in the original datasets, unlike this Dirac process. So a probability distribution function can be created using the Dirac equation, such that probability of outcomes is equally spread across all observed outcomes. You can tell by looking at the empirical distribution function here that if the value x is equal to one of the observed data points, then the result is 1 over m times however many times that same data point appeared in the dataset. For data observations coming from real measurements with very high degrees of accuracy, it may be the case that no data point is ever repeated. Nonetheless, the probability of each data point being the same doesn't mean there's no such thing as a trend. If many data points were clustered in one area, then generating data from the empirical distribution will also be more likely to yield values with many of them appearing in that one area, that cluster. Probability distributions can also be defined as mixtures of other distributions. This is typically done to create a distribution with behavior that can't be straightforwardly modeled by some existing distribution. What we'll call a mixture distribution works like this. You have a discrete set of distributions, each with their own parameters, and whatever the case may be. And that's a multi-Nulli or categorical distribution, where each one of those probability distributions is associated with a probability of being used. So when you generate a random sample, you first generate a random multi-Nulli variable, and that determines which probability distribution you'll actually be drawing from. Then you go ahead and draw a random number from that distribution based on its parameters. Based on all that, the probability distribution function for the mixture of distributions is equal to the sum of each distribution multiplied by the probability that a sample is taken from it. This concept reveals the important idea of latent variables. Latent variables are random variables that can't be observed. An example of this could be the random variable c that's present in the equation on the left. If you have a data set that is actually generated by the mixture distribution, then the random multi-Nulli variable c is obviously directly relevant to your data outcomes. And yet, you can describe the resulting probability distribution without reference to c. So that's why it's a latent variable. It's within the model, but potentially not observed. One special case of mixture models is the Gaussian mixture model. With a sufficient number of different Gaussians included in the model, a Gaussian mixture model can be constructed to emulate any distribution with an arbitrary level of accuracy. This makes sense because you could always just add many bell curves together to follow a curve with high accuracy when they're aggregated. One important concept is the idea of prior probabilities and posterior probabilities. The prior probability for a given distribution is the probability that the function will be selected for sampling when a random variable is generated. The key words are will be, since the sampling hasn't occurred yet. The posterior probability is the probability that a given distribution was selected to generate a random value. Keyword is was because the sampling has occurred. This example is a visualization of the output of a Gaussian mixture that generates two random variables jointly using a mixture with three components, bivariant Gaussian models. There are a couple of useful bits of information to take away from this by looking at each cluster. The first cluster at the bottom left is isotropic, meaning the variance is the same for both x1 and x2 in that multivariate Gaussian distribution. You can tell because the sample is basically circular. The cluster in the middle of the screen here indicates that the bivariate Gaussian is parametrized by a diagonal covariance matrix. The telltale sign of that is that the variance of the cluster is distinctly different in x1 and x2. The final cluster indicates that the component Gaussian is parametrized by a full-rank covariance matrix. The implication is that the variables x1 and x2 covary, and because it's full rank, it's really as if the variance is distinctly controlled, except not on the rectangular axes of x1 and x2, but instead on some other axes, which is generated by the eigenvectors of the covariance matrix. In this case, it would seem that the primary axis is a line going down and to the right. Having reviewed some basic distributions, the authors go over some functions which are useful and used often in machine learning applications. The first is the logistic sigmoid function. This function is useful for producing the phi parameter of a Bernoulli distribution. If you recall, the Bernoulli distribution outputs only 1 or 0, with probability phi of outputting a 1. So in machine learning applications, when you want to create some sort of recursive methodology where the arguments for these distributions are changing over time, you need to ensure that the variables of interest stay within the ranges that the function is defined on. In this case, the Bernoulli parameter phi must be between 0 and 1. And so the logistic sigmoid function is useful because for all real values, it stays between that range, with 0 and 1 being the limit cases at negative and positive infinity. This limit behavior is called saturation, and that term is used when small changes in the argument have negligible changes in the output. Another function is the soft plus function. It can be used to create the beta or sigma parameters of a normal distribution, because for all input values, it yields a result greater than 0. The authors also list a variety of properties of these functions, which I'll just put on the screen for anybody who may be interested. Feel free to pause the video to take a look at these. Bayes' rule is a function that proves very useful in many scenarios, allowing computation of certain probabilities, including conditional probabilities, given other information about those variables and their conditional probabilities. In particular, one use case for it relates to the mixed distributions reviewed earlier. Bayes' rule provides a means to determine the likelihood of having samples from a given distribution, given the sample output. Next, the authors present some things that are important to know, which are borrowed from the field of measure theory. The reason for this is that there are sets that can be created which create paradoxes when attempting to apply probabilistic computations to them. Measure theory gives us a way to box these cases in and identify them. One useful tool is the concept of measure zero. A set has measure zero if it occupies no volume in the n-dimensional space being described. For example, a line or a point take up zero volume in two-dimensional space, while a filled polygon takes up some positive volume. Following from this, almost everywhere is actually a technical term in measure theory. It's used to describe properties that hold true in all of a multidimensional space, except for on a set of measure zero. Essentially, the idea is that the theory can be safely implemented for many applications because the space where it doesn't hold is nearly negligible. The authors round off the review of probability theory for machine learning with looking at how to compute probabilities of variables when they can be expressed using different functions. This is about the idea that two different random variables are defined by distinct probability distributions, but those variables are also related to each other by a function, and that there must then be some relationship between the probability distributions themselves that has to do with the relationship between the variables. The relationship isn't as simple as the one presented on screen on the left, which is noted to be false. The reason for this is revealed when looking at the integration of the probability density function over the domain. In the textbook on page 70, an example is given that uses numbers, but I'll stick to the symbolic presentation here. Basically, the reason why that the expression on the left is false is that the infinitesimal used in integration with respect to y is not equal to that with respect to x. These can be understood as being different dimensions, different spaces. As such, a translation needs to occur between those two for the equations presented here to hold true. You could think of x space as taking up a different amount of volume than y space, and therefore the two infinitesimal values of integration are not the same. By operating under the preservation of the property denoted on the right, the proper solutions can be developed for the relationships between probability distributions for variables that are related by functions. These relationships are shown at the bottom, with one for higher dimensional functions shown on the right. That makes use of what's called the Jacobian matrix. That concludes the review of probability theory for machine learning. Fortunately for me, I was able to follow along with everything presented in the chapter, and it struck a nice balance between review and new ideas based on my past education. What remains of Chapter 3 is a review of information theory. I hope this was helpful. Thanks for watching, and take care.